So today we did synthetic division and the remainder theorem. So using synthetic division to solve is actually pretty quick. Okay, so the first step is to draw our synthetic division box. Okay, the number that goes on the outside is this x plus 5 set equal to 0. So it's technically a 0 of our equation, right? And that's the number that goes on the outside. Okay, then we fill in our coefficients of our exponents, of our variables on the inside. So, and we start highest to lowest. So we have 2, we have 6, we have negative 17, and we have 15. Okay, the first number always comes down to below our division box. We multiply on the outside and we add on the inside. Okay, so first we're going to have negative 5 times 2. Okay, and that's going to come right on the inside. So negative 5 times 2 is negative 10. Then we add those numbers down. We have 6 plus negative 10, which is going to get me negative 4. Then I have negative 4 times negative 5, which is going to go in here and give me positive 20. Then I add going down, and it's just a repetition of patterns. So negative 17 plus 20 gives me positive 3. Multiply on the outside, I get negative 15. Add on the inside, I get 0. This last number right here is my remainder. Okay, so here I don't have a remainder. My remainder is 0. Okay, which means when we have a remainder of 0, that means that this is a 0 of our function. So it will cross my x-axis at negative 5. Okay, we'll get more into that later on, but then to write my solution, we started with an x cubed, so my answer starts with 1 less exponent. Okay, so these are my leading coefficients. My problem started with an x cubed, so my answers are going to start with an x squared. And then we just decrease from there. Okay, so this is this long polynomial divided by this factor. Okay. If our function is not in standard form, we just have to rewrite it. So we'll have f of x equaled, we start with our highest exponent, okay, and we're also missing degrees. So we need to fill in those missing exponents with placeholders of 0 when we're missing an exponent. Okay, so if we're missing an exponent, we can't divide unless we have them all. So we need to incorporate that 0 in there, which is not changing our function at all, because adding 0 is allowed, but just giving us a placeholder. Okay, so then we continue to fill in those missing exponents. We're missing a 1. And just decreasing. Okay, once we have that, we can write our division box. The number that goes on the outside is x minus 1 equal to 0 and solve for x, so we get a positive 1. Then we write our coefficients in order. So we have 3, 0, negative 1, 0, and 2. First number comes down, adding on the inside, multiplying on the outside. Okay, so we have 1 times 3, which gets me 3. 0 plus 3 gets me 3. 1 times 3 is 3, minus 1 is 2. 1 times 2 is 2, 2, 2, and added together we get 4. Okay, so we do have a remainder in this case. So we'll just write our answer, one less exponent with these coefficients. And we'll just write our remainder over what we were dividing by. Okay, so if there is no remainder, then it is a 0 of our function. Okay, so my graph will cross at x equals -5. If there is a remainder, then not a 0 at, in this case, x equals 1. Will not cross x-axis. Okay, and once again, we'll get more into that later, but just so that you guys see that. Alright, so if you want to go ahead and pause this, this is a new definition, the remainder theorem, which works both ways. So if the polynomial f of x is divided by x minus c, then the remainder is f of c. Okay, also works with if divided by x plus c, okay, then remainder is f of -c. Okay, so whatever this value is going to be in order to make this factor 0 is what the remainder will be when we plug it in. Okay, so doing an example of that. Use the remainder theorem in synthetic division to find the functional value. Okay, so once again, we're just going to go ahead and do our synthetic division. So -2 is on the outside. Fill in our leading coefficients. Multiply on the outside and on the inside, bring the first number down. So we have -2 times 3, which is -6. Adding is -5, 10, 11, -22. So we get a remainder of -27. So it says that since we're dividing by x plus c, then f of -c is going to give me my remainder. Okay, so we check by plugging into original function. Okay, so using our original function, we will have 3 times -2 cubed plus -2 squared plus -2 minus 5. Okay, so -2 cubed is -8, -2 squared is 4, minus 2 minus 5. -8 times 3 is -24 plus 4 minus 7. So we get -20 minus 7, which gets me -27. Okay, which is exactly what the theorem stated. Alright, so going backwards using this function, find f of 4 and then verify using synthetic division. So we would just plug 4 in for x. Okay, so 4 to the 4th power is 64, I believe. 4 times 4 times 4 times 4. Oh, 256. Minus 12 plus 5 gets me 249. So it says that when we use synthetic division with this polynomial, we should get a remainder of 249. So our leading coefficient is 1, and then we don't have a cubed, we don't have a squared, we have a -3 and a 5. The number that goes on the outside is 4. Okay, so it's the same number as whatever we would use to find our remainder using the remainder theorem. Okay, so first number comes down, multiplying we get 16, 16, 40, 64, 64 times 4 is 256, 256 minus 3. Adding that together, I get 253. This is definitely not correct. Oh my gosh, this was supposed to be a 1, people. Okay, so brought down the 1. This is a 4. Adding, now this is 4. This is 16. 16 times 4. Now that's 64. 64, 61. 61 times 4 is 244. Added together is 249. Oh my goodness. So, our remainder, working the other way, was proven by putting f of 4 into the original function.